Hello. So it's only 5 people so far. Okay. All right. Should we get started? Well, we'll do a review. Hopefully people will join. All right. Can you guys hear me? Say yes.
Yes.
Okay. All right. Okay. So let's briefly review what we did last time. We talked about the barrier method some more. In particular, we did an example to confirm at least that the barrier method actually works. As you let epsilon k go to 0, you do get to the solution to the original problem. And then we talked about another method that's useful. So the barrier method is useful for inequality constraints, and another method for computation method for solving problems with equality constraints is the penalty method. And the penalty method, you add, typically you add a quadratic penalty on the constraint, right? So when you violate the constraint, there's a quadratic penalty that you incur, and you let this coefficient multiplying that penalty go to infinity, so that when k gets large, this becomes less and less relevant for minimizing the sum. Okay, so that's the idea. And then we did, and we proved that that actually works. And then went on to do an example to illustrate that it does work, right? So that's what we did. And then we started a new topic, which is duality. Okay. So basically, this is a Lagrangian. This is also called Lagrangian duality, because what you do is you take the Lagrangian function, right, and you create a function of the Lagrange parameters by minimizing over x, minimizing the Lagrangian function over x to get rid of the dependence on x. And then what you're left with is a function of just the Lagrange parameters, and this is called the dual function. Okay, and of course this dual function is basically defined for the equality constraint Lagrange parameters. They can be positive or negative, so they belong to Rm, but the ones corresponding to the inequality constraints are restricted to be non-negative, right? So this is a constraint set over which this dual function is defined. And the duality result, first of all, we show that this function is always concave, and so an optimization problem involving this function d is always going to be a convex optimization problem, right? Because the negative of d will be a convex function. And then we saw in particular that if you do go ahead and maximize this over the parameters under the constraints that the mu's have to be non-negative, then if you solve that, then the value that you get, the objective that you get at the optimum is always going to be less than or equal to the optimum value for the original constraint optimization problem. So this will the dual function, maximizing the dual function provides a lower bound. Actually, even if you don't maximize it, take for any value of lambda and mu that satisfies mu positive, this will provide a lower bound. And this is the tightest lower bound by maximizing over lambda and mu. You get a tightest lower bound on the original optimization problem. Okay, so that's what we showed, that this holds. Not that hard to show. But then I mentioned at the end of the lecture that in some cases you have equality here. So the dual problem, which is a convex optimization problem, always a convex optimization problem, actually has the same solution as the original optimization problem. Okay, so today we'll study conditions, some basic conditions under which we have that kind of equality. That's called strong duality. Okay, any questions? Any questions about what we did? Things, any other stuff that we have done so far. If you have any questions, time to take that now before we start talking about strong duality. Okay. So that leads us to this. So again, I remind you that the F here is the feasibility set. So X satisfies the equality and inequality constraints. And we write the inequality constraints compactly. We talked about this before. This could be multiple functions being less than, or all the GJs being less than or equal to 0 is written compactly like this. All the HIs being equal to 0 is written compactly like this. And we could have some other set S. And typically, when this set might correspond to the set of values of X for which the functions are well defined. Right? So the domain corresponding to the domain of the functions. Okay, but if the functions are well defined over all of Rn, then this set will be Rn. Okay, typically. All right, and then you can define the Lagrangian like this, and we saw that the dual function is defined like this. Okay, and the dual function has these constraints on it. Okay, so we saw the weak duality result, and now we say that under some conditions we have equality. So this is called the primal problem. The problem that the original optimization problem of F over sorry, this should be minimizing. This is a typo here. Righto. It should be. So this is the primal problem. And this is the dual problem. Okay. This also, I don't know, okay. All right. So so the result we're going to prove is that there's some conditions under which this equality holds. And the conditions that we'll first study are the simplest conditions, and the conditions under which it's the easiest to prove duality. Okay, and then I'll mention some other slightly more general conditions. And in fact, there's been a lot of work on duality, and as I mentioned last time, I could teach a whole course on this if I wanted to. There are books written about it, and so in specific applications, okay, even if the conditions that I described in today's lecture don't hold, you might still be able to establish strong duality. Okay, but you have to do it on a case-by-case basis in some sense. Right. So let's look at the conditions. And we actually encountered these conditions in a lot of the examples that we did. So if F is convex, the HIs are affine, or linear, if you want to think of it just as linear plus a constant. And the G's are convex. G's are convex. I don't know how to write those today. Okay, I'll fix this in the final version. And the set S is Rn. So there are no other, there are no other constraints, right? Other than the ones from the equality and inequality constraints, and the functions are defined. I mean, on Rn. So there are no issues with domains. Okay. So in that case, now if X star, so actually these conditions hold. F being convex, HIs are affine, and G's are convex, then the Lagrangian is going to be convex, right? We saw that over Rn. Okay. Now, if X star is an optimal solution for the primal problem, okay, and one way to obtain that optimal solution is by taking and setting the Lagrangian to 0 because we have convexity, right? So X star is an optimal solution for the primal problem. X star is regular. And lambda, and now I'm going to put a star on the lambdas, okay, on purpose, because these lambdas will turn out to be optimum for the dual problem, right? So if lambda star and mu star are the corresponding Lagrange multipliers, then strong duality holds, and lambda star mu star maximizes this function. Okay, so again, if it's a nice convex optimization problem, and there are no other constraints in S. So S is equal to Rn, okay, and the problem is regular, right? So that I can actually solve for gradient of the Lagrangian equal to 0, then basically I have a strong duality. Okay. All right, so let's prove this. So any questions about the statement, the result, and the assumptions? All right. So first of all, as I just mentioned, from the regularic assumption and the first order necessary KKT conditions, we get that the gradient of L at X star, gradient with respect to X, right, of at lambda star mu star is equal to 0. So this is the KKT condition. Okay, assuming regularity. And we also know that the complementary slackness conditions hold. So let's put those down because we'll use them in just a second. Okay. All right. So that you get by regularity. Now, since F is convex, HIs are affine, GJs are convex, then we know that L is convex in X, right? For that fixed lambda star mu star. Therefore, if you by 1, if you just plug in 1, we know that this is the minimum because gradient equal to 0, since we have convexity, the gradient equal to 0 guarantees that we have a minimum. X star is the minimum. So L of X star, lambda star mu star is the minimum of L X over all X, basically. And if you want to say X belonging to Rn, if you want. Lambda star mu star. Yeah, in fact, we exploited this in the examples, right, that we did in class and the ones in your homework, right? All right. and that's how we got the second order sufficiency condition. So, but this is a particular value of lambda and mu here, lambda star mu star. So if on the right hand side I look at the value that maximizes this quantity, right? So this should be less than that. So I make this less than the max over lambda mu belonging to the constraint set C, where the mu's are all non-negative, minimum over x, Lx lambda mu. Okay. So this L of x star lambda star mu star has to be less than this max min of the Lagrangian. And we'll call that equation 3. All right, so now let's actually take the same quantity and look at it a different way. So I'm going to look at the same L of x star lambda star mu star and look at it from a different perspective. So what is this? This Lagrangian is, let's write down what it is, f of x star plus lambda star transpose h of x star plus mu star transpose g of x star. Right? Okay. But let's look at h of x star. This is equal to 0 because x star satisfies the constraints. This guy, but what about the second term?
Less than or equal to 0.
Well, we just saw that by complementary slackness, it has to equal 0. Right? So this is also equal to 0. By the condition, the complementary slackness condition we just wrote. So this is actually just f of x star. Okay, so now I'm going to look at how this is related for arbitrary lambda and mu. Okay, so what I'll do is now I claim that this is bigger than f of x star plus, now instead of lambda star, I have an arbitrary lambda transpose h of x star plus arbitrary mu times g of x star. Why is this true? Well, this is true because this guy is equal to 0 still. This guy is less than or equal to 0, and this guy is greater than or equal to 0. So when you take the dot product of those two, you'll get something that's less than or equal to 0, right? That's not positive. Right. So when I add something that's, this is the first term is 0, and I'm adding something that's not positive to this, then fx will be greater than this side. This holds for all mu lambda belonging to this our constraint set, all mu positive, right? Okay, but so this is L of x star lambda mu. So L of x star lambda star mu star is bigger than or equal to L of x star lambda mu for all lambda mu belonging to constraint set. So since this is true for all, it's also going to be true when I take the maximum. It's true for every choice of lambda and mu. So it's going to be true for the choice of lambda and mu that maximizes this. but that's a particular value of X star, right, that I have on the in this thing here. This is a particular choice of X. So if I minimize over X, then I'll get something smaller. So this should be larger than minimum over X max. Let's call that 4. Okay, so
X
yeah.
in L. The argument should be X.
Yeah, minimum over X. Yeah. Is that your question? X should be not an F, but just a minimum over all X. X and Rn. Right?
Wouldn't it need to be X instead of X star in the Lagrangian?
Oh, yeah. Sorry. Okay, that's what you were saying. Okay. So the minimum over X, and the X should be here. That's right. Sorry. Okay, so now let's look at these two equations that we have here. This first equation says that this L of X star, lambda star, mu star should be less than the max, less than or equal to the max over lambda mu, min over X of this. Okay, and then we showed that the same thing has to be bigger than min over X when these, the min and the max here have been swapped of the same quantity. Okay, so if we combine these two equations, this L of X star, lambda star, mu star gets sandwiched in between these two quantities. Okay, so let's write that down. So L of X star, lambda star, mu star is less than this thing and bigger than this thing we just showed. Okay. All right. Now, here's a general result. If you look at a function of two variables with some constraints, script y and script z, so g, y, z with these constraints, and if I look at the max min of this function of these two variables, it's always going to be less than or equal to min max. And this is very easy to show. I'd like you to do it in homework 5. So max min is always going to be less than min max. Okay, but what this equation 5 says is that the min max is less than max min. This is always true, and we have this, right? So by the lemma, we have that the max over lambda mu c belonging to c, min over x of this is less than the min max of L x lambda mu. So if we compare equation 5 and 6, okay, what we have basically shown is that the left-hand side has to equal the right-hand side. And this value gets sandwiched in between, so it has to equal this value as well. Okay. So what we have shown is that the max min is equal to the min max, and those of you who are interested in taking more advanced courses related to this topic, this basically is a special example of what's called a min-max game, right? And when max min equals min max, the game, you can think of it as you have an objective function, and one guy is trying to minimize this thing, and the other guy is trying to maximize the same thing, right? So that you can think of playing a game with an adversary, where this is the reward that you're getting, and the adversary wants to minimize your reward, and you want to maximize your reward. Okay, and when this equality holds, that game is said to have what's called a saddle point solution. Okay, and that saddle point solution corresponds to an x, an optimum value of x, and an optimum value of lambda and mu And actually, that turns out to be this thing here, x star, lambda star, mu star, that we get from the first order KKT conditions. Okay, so this x star, lambda star, mu star is said to form a saddle point solution to this min-max game. Okay, so but you don't need to know about that necessarily. I just wanted to let you know that this problem really has that kind of more general interpretation in the context of min-max games. Okay, so any questions? We aren't done yet, but any questions so far? We haven't proved that duality holds. We're going to use this saddle point solution to show that strong duality holds. But any questions about getting to this step? Or is it clear? By the way, this result here, this lemma, which you show in homework 5, is very, very easy to show. It's just, you know, a sequence of doing the min and the max on the left and the right hand side, and it's pretty straightforward. Okay, just a couple lines. Okay. All right. So what does this mean? So let's actually examine this quantity here. This max over lambda mu of Lx lambda mu, right? So it's the max this is the max of let me write down the Lagrangian. So it's f of x plus lambda transpose h of x plus mu transpose g of x. Okay, so now let's look at this quantity here. So suppose one of the components of this h of x, one of the hi's of x, is non-zero, so it doesn't satisfy the constraint. Then what's the maximum value of the sum? You're maximizing over all lambda belonging. Each of the lambdas can take values in the whole real line, and one of these guys is non-zero. Say one of the hi of x's was -2. Then what is the maximum value of this?
Infinity.
Infinity, because I could always take my lambda, that lambda, to -infinity until this thing will blow up, right? So there's no maximum, right? Maximum infinity. Same thing here. These mu's are non-negative, right? And so what happens if one of these guys, so I can make them as large positive value as I want in this maximization. So what happens if one of these g's happen to be not less than or equal to 0, but bigger than 0, some positive value? So one of the gj of x's was +2. Then by taking that corresponding mu parameter to infinity, I can make this max go to infinity, right? So basically the maximum only makes sense when you're in the constraint set. So this maximum is infinity if x, I should say, if x does not belong to the constraint set. And if it does belong to the constraint set, then what happens? Then if it belongs to the constraint set, then what happens is that if it belongs to constraint set, this will be negative. This is, sorry, less than or equal to 0, and this will be equal to 0. So then the maximization of this is the same as the maximum value of f of x. Right? Because this guy, these won't matter in that case. Right? The maximum value is basically going to be f of x. because this will go away, and this will be something less than or equal to 0. So so what you would do is basically make the mu's all 0, and then the maximum value obtained will be just f of x in that case. So now, if you're looking to minimize this quantity, right, then you really it's because the minimum value really only makes sense. You really need to only consider x belonging to f, because for x that's not an f, the value is infinity, so it shouldn't affect the minimum. So if I take the minimum over x, the minimum over x can be restricted to only the feasibility set f, and in that case we know that the max value is just nothing but f of x. So the min over x, the max over lambda of the Lagrangian, is nothing but the minimum okay, and this is the original optimization problem. So this turns out to be just nothing but the original optimization problem. Okay, so that's, we've dealt with this part here. So the min max of L is nothing but the original optimization problem. Now let's look at this. Okay, so this we actually already know, because the min over L x of this is the dual function. So let's actually write that down. So the min over L is what we define to be the dual function. So this is the max over lambda mu, the dual function. So basically what we have shown is that the max over lambda mu is when which is what we wanted to show. Okay, so strong duality holds. Okay, the other little piece that we need to finish this argument is that is what that saddle point corresponds to. Okay, and that saddle point corresponds to, we saw this already, right? So this max of the d lambda mu is this. Okay. But this is d of lambda star mu star, because x star is the minimizer, right, for lambda star mu star. So this means that lambda star mu star solves the dual optimization problem. Okay. So any questions? So what's the advantage? Okay, so if you had all this nice convexity and stuff, maybe you should have just gone ahead and stuck with the primal problem. Why would you bother with the dual problem? The advantage is that sometimes the dual problem turns out to be easier to optimize using computational methods. and also conditioning might be better. Okay, and we'll see something related to that on next Thursday, I guess, when we talk about augmented Lagrangian methods. Okay, so that's an advantage. And it turns out that in some applications, you might be able to show that strong duality holds, and sometimes they call that another way to say that is that there's no duality gap. Okay, even when these convexity conditions don't hold. In that case, of course, then there's a big advantage of working with the dual problem, because that's always a convex problem. Okay, and I hope that some of you who are taking the course for credits and your projects, you're going to come across problems like that in your research areas where that holds. Okay, one place where you see this kind of stuff is in optimization and power systems. Okay, so those of you who are in that area, you may want to take a look at papers on that topic. Okay. Now, this strong duality result, we proved this for the case where that constraint set S was equal to Rn. So there were no other constraints essentially other than the equality and inequality constraints. But actually the result holds more generally, and this seems like a slight generalization, but it turns out to be very useful in many practical problems, because mainly because of domain issues. Okay, so you can generalize this to S being any convex subset of Rn. So it doesn't have to be equal Rn, but it can be any convex subset of Rn. But in this case, you need to check another condition. Okay, so you need the existence of a point X that's in what's called the relative interior of S, such that the constraints actually hold in a strict manner. So the inequality constraints hold strictly, and the equality constraints hold. Okay, what's a relative interior? I didn't go into these kinds of details in this course. If you want to see more about things like this, read the book by Boyd and van der Berge. So relative interior, if S is actually a subset of Rn that's not contained in some smaller dimensional space. Okay, think of say if you have say three-dimensional space, and you have a circle, a filled-in circle, right? A filled-in circle that's two-dimensional. It's not a sphere, but it's just a two-dimensional circle, right? That's in three-dimensional space. So that's a convex set. That's a convex set, but it's in a lower dimensional space than the original space. Okay, and the relative interior of this convex set is basically defined with respect to this lower dimensional space, and through what's called an affine hull, which again, these are technical things that I'm not going to go into here. So, but if this set S, subset S, was actually not embedded in a smaller dimensional space, but it was sitting in the original space, then it's the same as the interior. Okay, so which we defined before. Okay, but you basically need the existence of this X, and the proof that strong duality holds actually uses that condition very explicitly, and its proof is much more involved than the proof I just gave you, which was based on this min-max game. So I'm not going to go into that, but if you want to see the proof, and the best version of that proof that I've seen is in the book by Boyd and van der Berge, so which is one of your references, so you can take a look at it there. Okay, but this actually, what I just proved, the conditions that I gave you, the convexity conditions with S equal to Rn, and this when S is some convex subset of Rn. These conditions are together called Slater's conditions. Because the result that I just gave is a special case for which the proof is much easier. Right? That's called Slater's condition for strong duality. Because he was the first one to prove this, I guess. Okay, and they also call Slater's constraint qualification conditions. Okay, the more accurate term. Okay, so everyone kind of understand where this is coming from and when you can easily show strong duality holds. Right. So you need basically you need the convexity of essentially the convexity of the Lagrangian function to be able to prove things, but you also need so S is not of all of Rn, then you can run into some issues. So you need to do another little condition, okay, in order to be able to prove things. All right. And another interesting fact is that if you have a linear program is a special case of a convex program, right? So a linear program has a linear objective function and linear constraints. Okay, linear constraints and the constraint functions are going to be convex, and the equality constraints are affine, so that's not a problem. All the conditions that were restated here will hold for linear programs. These conditions here will hold for linear programs. But we also saw something before for linear programs, and we saw that we have Lagrange multipliers will exist even when we don't have regularity, right? I mean, so how to deal with that, right? So you get rid of certain, essentially you can think of it as getting rid of certain constraints that are the problem, that make the problem not regular, and so regularity doesn't really come into the picture. So you can actually drop this regular condition, and so as long as the linear program is feasible, then its dual, the dual is also going to be feasible, and strong duality holds, right? Because all these conditions are met, even without regularity. So that's the only slight twist with the linear program. Okay, but otherwise, basically, it's a special condition, a special case of the proof we just gave for strong duality. Okay, it's 11:42. So maybe we can take a break now, and then I'll show you what the dual of a linear program, a general linear program, looks like. Okay. And you're always guaranteed that strong duality holds. Any questions? Okay. Sure. All right. So let's take a short break, and then we'll come back at 11:45 and talk about linear programs. All right. Any questions that you thought of over the short break? All right. So let's actually talk about the dual of a linear program now. Okay. So this is a linear programming problem in what's called standard form. So it turns out that you can take any linear programming problem that involves both inequality and equality constraints and write it in this manner. And if you want to see the details of that, it's in Boyd and Vanderburg's book. Okay, but I'm not going to focus so much on that because I don't want this course to be about just focus too much on just linear programming problems. So, but it turns out that you can always do this. So even if you have inequality constraints that involve matrices, you can basically get rid of them and absorb the matrices into the equality constraints and into this vector C that defines the linear objective function. So the objective function is linear, and you have equality constraints here, and this is an inequality constraint. So that's a general, what's called an LP in standard form. Okay. So let's take this LP in standard form and look at its dual. So let's find its dual first. Right. So the dual function is given by the minimum. Again, there are no other constraints, so it's a minimum x belong to Rn. And you don't have to worry about domains because all the linear functions, the domains are Rn, no problem. Okay. Plus the equality constraint, let's that we're going to multiply is lambda. Again, as we said before, we don't have to worry about regularity with linear programming problems. Okay, so we get that. A minus sign because this was x bigger than or equal to 0, so I have a minus in front of me. Okay, so let's rewrite this. Take all the terms that involve x. So I get C transpose plus lambda transpose A minus mu transpose X minus lambda transpose B. Okay, so let's look at so you're minimizing this over X belonging to Rn. So this is similar to the argument we just used in the proof of strong duality. If this is a vector, this is a row vector. If any of the elements of this row vector is non-zero, then what's the minimum over X of this function?
Minus infinity.
Minus infinity. So basically the minimum doesn't exist. It's non-zero. And what if it is 0, but it is 0, it disappears. If this is 0, it disappears, all you're left with is this. If this quantity is 0, the same thing, transpose. But if this is the row vector, I can convert it into a column vector by taking its transpose. So this is the same as saying that C plus A transpose lambda, which is a transpose of lambda transpose A, plus, is equal to mu. I'll take the mu to the other side. Okay, so now we're ready to write the dual problem. So the dual problem is to maximize this lambda transpose B. And the only values of lambda that you care about are the ones that satisfy this equality, right? The ones that satisfy this equality. So we'll put that as a constraint in my dual problem. So you want to maximize minus lambda transpose B such that, of course, lambda doesn't have any other constraints on it, but mu has to be positive, or not negative, sorry, each of the components of mu. And we have the constraint on lambda, the equality constraint, plus C equal to mu. But if you look at these two constraints together, it can be written jointly, because the objective function does not involve mu, right? The objective function here does not involve mu, it just involves lambda. So I can combine these constraints because it's only the constraints that I have mu. And so these two constraints together can be written equivalently as A transpose lambda plus C is non-negative. So we end up with the dual problem as maximizing negative lambda transpose B is the same as minimizing lambda transpose B. Subject to the constraint that A transpose lambda is bigger than minus C. Sorry. I'll just write it plus C is bigger than 0. So it's better because it's a vector. So it's better to write this. A transpose lambda plus C greater than or equal to 0. But what happened here? So we know that the solution to this dual problem is the same as the solution, and the value at least is the same as the value of the original problem. But there's an interesting difference between these two. And what is that? So you look at this problem. This had equality constraints and inequality constraints, whereas this problem has only inequality constraints. It's also a linear programming problem, but it only has inequality constraints. What's the advantage? Having only inequality constraints? See, I'm claiming that any linear program with both equality and inequality constraints, if I look at its dual, right, and solving the dual is the same as solving the original problem, at least in terms of the value that you get at the end, then what's the advantage of having only inequality constraints? Anyone can think of something based on what we've studied so far?
The Lagrange multipliers are non-negative?
Well, but I mean, no, well, that's not quite. I mean, it's related, but it's not quite the right answer. But think of computational techniques that we've studied.
You can use the barrier method?
Yes, you can use the barrier method or interior point methods, right? And this was the reason I mentioned that the barrier method was most famously applied to linear programming problems. And the way you apply to a general linear programming problem is that you can start with a general linear programming problem of this form, look at its dual. The dual only has inequality constraints, and so you can apply the barrier method there. So that's why its barrier method has been so powerful, and also called interior point method for linear programming problems. Okay. So any questions about this? And by the way, the linear program also has another interesting property, and you're going to show this in your homework. If you start with this linear program with only inequality constraints and take its dual, you get back a program that looks like this with both equality and inequality constraints. So the dual of a linear program is the original program. Okay, doesn't hold more generally, but there are other kinds of duals of functions for which these kinds of properties hold. Okay, and you might study that in other contexts. Actually, it's similar to something that you saw in linear systems as an undergraduate student, right? So, what is something that you might have seen in the context of linear system that looks like this, where you do an operation and do the operation a second time, you get back the original thing. Anyone? Any kind of transformation operation that gives you
it's a projection. Idempotent.
Yeah, that's actually a good example. I was thinking of Fourier transforms. Yeah, but that's
okay.
You take a Fourier transform of the Fourier transform, you get back the original function with scaling, of course. Yeah. All right. Okay, so now let's do another example to illustrate the strong duality, and we'll actually establish that actually strong duality holds for a specific example. And I might make you do one more of these kinds of things in your homework. So this is actually from homework 4. This is an optimization problem you solved in homework 4. This quadratic function with linear constraints. And we showed that x star, which is 1.5 and 0.5, is the global minimum for this optimization problem, with mu star as equal to 1, 0. And if you actually compute the value of the function at x star, it's minus 5/2. That's not hard to see. Okay. So let's look at what the dual of this convex program is. Okay. So this actually satisfies all the conditions for strong duality, right? You have a convex objective function. There are no other constraints due to the domain is the entire R squared for these functions, and you have linear which is a special case of convex functions G, right? Okay, so so if you look at this, I can look at the Lagrangian that has two parameters, mu1 and mu2, and I can combine things. So this is x1 squared plus x2 squared plus mu1 plus mu2 minus 4 times x1, and then I get plus mu1 plus 2 mu2 minus 2 x2, and then the constants that remain are 2 minus 2 mu1 minus 3 mu2. Right? And we know that this Lagrangian is convex. Why is it convex? You can look at the Hessian if you want, but yeah, the Hessian is the identity matrix, right? It doesn't matter what's sitting here. That's literally determined by the second order terms. The Hessian is an identity matrix. So this is a strictly convex function. So we know that the minimum satisfies and you you can use the gradient. So the gradient will be 2x1 plus mu1 plus mu2 minus 4 equal to 0. And then the second one is 2x2 plus mu1 plus 2 mu2 minus 2 equal to 0. And you can solve this to get x1 is okay, so we have our solution for x star essentially, right? Okay, so we have the solution for x star that minimizes this, and so we have the dual function from that, right? So the dual function, you just plug in these x star values. Maybe just put a star on this. So plug in the x star values into this. Okay. So you get this as the dual function. Okay, this is x1 squared, x2 squared minus this thing here. So why do you get that? Because basically x1 squared is this squared, and then this mu1 has the same, essentially has the same term, x1 plus here x1 is mu1 plus mu2 minus 4. This is the same thing as x1 squared with a negative sign, but it's twice as large because this is divided by 4 and this is divided by 2. So you just get the negative of mu1 minus mu2 minus 4 squared divided by 2, and the same thing with this term, and then these terms will remain. So this term and this term get combined, this term and this term get combined, and you end up with this expression. Okay. So this is a function of mu. Okay, and this is, it's not hard to see that this function had better be a concave function. We know that it's always going to be a concave function, right? And we can actually look at the Hessian to make sure that it's concave. So the maximization of d mu, which is the same as the minimization of negative d mu. So the negative of this function is a convex function. Okay, so it's a convex optimization problem. And you can take the compute the gradient and the Hessian. That's not hard to do. Mu1 minus mu2 minus 1, and this the gradient with respect to the second guy with respect to mu2 will be mu1 plus. So you can work this out. 3 over 2 mu1 minus 5 over 2 mu2. Actually, there should be a plus 1. Yeah. Okay. So, and then you take the Hessian by computing another derivative, and the Hessian actually just turns out to be minus 1 minus 5 over 2, and then 0 on the diagonals. And this is clearly negative definite, right? It's negative definite matrix. So it's a strictly concave function. D of mu is a strictly concave function, or negative d of mu is a strictly convex function. So we verified that that's true. Okay, and now we can solve this. This is a constraint optimization problem, right? So you can solve this problem. It's a constraint optimization problem. Again, the way you would solve it, if you want to solve it analytically, is to apply solve this using Lagrange multipliers, right? Because since you have these constraints, you have to take that into account. And it turns out that the minimum for this problem occurs on the boundary. And we actually kind of already know this, but Okay, I'll leave that as an exercise to you. So start with this quadratic function with these linear constraints and find the optimum solution to this problem using KKT conditions. Okay, and that solution turns out to be, what do you think the solution is? I'll let you do it at home, but what do you think the solution is based on our strong duality result? Let's go back to what we did in homework 4. Where is that? Oh, that's here. What did we show in homework 4? We showed in homework 4 that x star is this with mu star is 1, 0. And our strong duality result says that this should be the solution that maximizes the dual function or minimizes the negative dual function. Okay, so, and it's a boundary. It's on the boundary because this guy is 0, mu2 is 0. So it's not hard to show that this mu1 star is 1 and the mu2 star is 0. Okay, again, do this at home. And then if you compute the value at mu star of this function, so plug in, if you plug in mu1 equal to 1 and mu2 equal to 0, you'll get minus 3 divided by 2 squared is minus 9 over 4 here, and here you get 1 over 4, minus 1 over 4 when you take the minus sign here. And then you get this canceling out of this, and this is 0. So it's minus 9 over 4, minus 1 over 4. Okay, which is minus 10 over 4, which is minus 5 over 2, which is f of x star. So we just verified that strong duality actually holds. Okay, so the maximum of D is the same as minimum F. Right? Any questions?
And if you are interested in argument rather than the value, then we can just plug in this mu1 star and mu2 star to the x1, x2 expressions, right?
Can you repeat that question? I didn't get that.
So yeah, if we are interested in the argument, like the x star,
oh yes,
rather
yes,
than f of
yes.
x star.
Yes, that's a good point. Yeah. So if you're choosing to solve this using the dual, and then you need to go back and find the argument. Yeah, you can do that. That's right. All right. Oh, we still have a few minutes. I didn't expect to finish so early, but any questions? Is it clear how we got this mu stars here? I mean, I didn't go through the steps because it's like a problem very similar to the one you just did in the homework, right? This is a quadratic function with linear constraints, and it's to the KKT conditions, just a couple of lines, and then, but you do. You have to call the Lagrange multiplier something else, and maybe nu1 and nu2, and then you have to consider 4 cases again if you want to do it all correctly to solve this problem using constraint. But the whole point of this exercise was to show that in this example, strong duality holds. Okay, but not to actually use the duality result to solve the optimization problem, because we already have a solution to the optimization problem using the KKT conditions.
So what's the difference between the strong dual and the weak dual in the last lecture again?
Weak duality just says that you'll always have weak duality, no matter what type of optimization problem you're looking at, right? So you'll always have this always holds. So, yeah. So this condition always holds. right? So if you want to just get a lower bound on the optimum value, okay, then you can actually, you don't even have to solve this maximization problem. You can get a lower bound by choosing any Lagrange multipliers here in d lambda. So in d lambda mu. Okay, but of course, to get the tightest lower bound in that case, if when strong duality doesn't hold, you'll take the maximum over this. But this result always holds without any other conditions. Okay. So when we say strong duality holds, we say that we need some conditions, but under those conditions, we can show that these two are equal to each other.
I see. Thanks.
All right. Well, maybe I should use this time to discuss your project. If you have any questions about the project, I'm going to post something on the website soon. I just want to make sure that you're not going to have. It didn't make sense for me to ask you to start reading papers without actually covering a significant amount of material in class. Otherwise, those papers may not have made much sense to you. But hopefully now that we have covered duality, many of those papers where you apply optimization in your research areas just at least make some sense to you. So then you could describe them in your own words. So the idea behind the project is for you guys to form teams of up to 3 students, and then write pick some optimization problems, some key optimization problems that arise in the context of your own research, and explain how optimization theory tools were used to solve those problems. You don't have to solve them yourself. I mean, these are things that have already been done, but I just wanted you to explain in your own words how tools from optimization were used in the context of your research area. But I'd like you to find papers on your own. And if you need to discuss something about the papers, if you have some questions, then you can ask either me or one of the TAs in the office hours. Okay. But that'll be something that'll be due at the end of the semester. Maybe I'll make the due date the same as the date of your scheduled final exam, which you're not going to have. You're not going to have a final exam this semester. And there'll be another computer assignment, and that will be due on the last Monday, last week of classes, which I think maybe December 7th or something like that is a Monday. So that's when you'll have a third computer assignment. Okay. Any questions? Okay. Oh, and the report, I would keep it quite short, maybe 5 pages at most. If you want to put it in like a 2-column conference paper format, you can, or a format that looks a lot like what you might use in your qualifying exam, right? Just use a standard 2-column conference paper format to write your report. Okay. Okay. No other questions. I guess you guys are gearing up for the election, right? Next Tuesday. So
Already voted.
if any of you are eligible to vote, you should probably go do early voting, because it's much easier than doing it on Tuesday. Although I think the chancellor gave Tuesday off so that you can go. I think there's an early voting place on campus, right? For those of you who are here. But it's much easier to do. I did that last week in a place in Champaign, and it was much easier than waiting in line on Tuesday. So But in any case, Tuesday is off, so I'll see you guys on Thursday.
Oh, I have a quick kind of non-specific question.
Yeah.
I feel like in engineering, we're always talking about like big problems that you need to use computation to solve an optimization problem.
Yeah.
But are there any interesting examples in like physics or math where there are analytic solutions that you would get by looking at the dual?
Physics or math. Okay.
Like some kind of physical problem. I know that there's like
yeah. So I mean, I give the example and use of power systems. That's one area where I've seen this really applied effectively, where you could show that there's no duality gap, and that's what and the dual problem, even though the original problem was not convex, that you find the problem, the dual problem is convex, and it's much easier to solve. But there are many other examples. I mean, I don't know of them at the top of my head, but if you search on Google Scholar for in fact, the title of the papers probably also have that term in there, that something about duality gap, and so it might be, and where you actually can really exploit the convexity of the dual problem to get computationally tractable solutions.
Okay, I'll try to find something.
Yeah. But if I find a really good prototypical example of that, I'll let you guys know.
Okay, I'll stay tuned.
All right. Have a good weekend.